Welcome to Biomaterials. So what are we going to be talking about today? We're going to be talking about strategic surface modifications, and in particular, we're going to talk about chemical modifications to surfaces. So unlike last time when we talked about plasma treatment, how there's this sort of battering ram approach to just generally make a surface more hydrophilic, today we're going to be talking about how to add particular chemicals to a surface. You know, what sort of strategies do we have? What types of chemicals do we use? And things like that. So we're going to start off with talking about some applications. Right? What are some applications where we choose to add particular chemicals to a surface? Then we're going to talk about the general goals that apply to almost all of these applications. Right? What goals might we have that are sort of common to most of these applications? In the process of attaching particular chemicals to a surface. Then we're going to talk about examples of the chemistry. We're going to sort of talk about the general idea of the chemistry involved. So the general idea of the chemistry involved. And then we're also going to talk about, after that, we're going to give particular examples of commonly used functional groups. So basically, what is the toolbox of chemicals that we have at our disposal to accomplish this sort of the process of attaching one or more chemicals to a surface to accomplish our general goals in these specific applications. And in particular, these functional groups, they're like Legos, where there's sort of like, you know, one part and another part and they attach together. So we'll frame the example. We'll not just say, okay, here are a bunch of chemicals, you know, good luck. We'll basically say, hey, here are a bunch of chemicals and here's their interactions. Basically, what binds to what else, what doesn't bind to what else. And this will sort of serve as a framework where you can find a sequence of chemicals to add to, you know, one after another to eventually attach your desired chemical to the surface. And then we'll sort of end with a bit of a recap of some of these ideas. And the two main ideas that we're going to think about in our recap is the importance of concentrations in some of these steps, right? The importance of concentrations of various of these chemicals, right? So there might be, you know, what happens if the concentration of chemical X is too low? What happens if concentration is too high? How does that impact some of these factors, right? Some of these general goals or the chemistry involved. And the other thing we want to talk about is the importance of the order of operations. Right, so if we have like chemical A, chemical B, chemical C that are involved in this process of eventually attaching one desired chemical to a surface, well, you know, like does it matter if we do ABC, CBA? Does it matter if we do ABC to the surface or ABC to the desired molecule or CBA to the, you know, desired molecule? Like, how does the order impact the eventual functionality or the eventual quality of the attachment of the molecule to the surface, the function of the molecule that we attach to the surface, etc. So this is our general plan for the lecture today. So let's start off with talking about some applications. So take a moment now. If you have maybe in a co-op or internship or some research, if you have some experience talking about applications, right? Maybe you're familiar with some applications where you wanted to attach some particular molecule to some particular surface. You know, put it in the comments below or just carefully consider it and, you know, discuss. So I have a few applications here that I'm going to talk about. So one application, the first application that I'm going to talk about is in what are called plug flow reactors. So this is these plug flow reactors are something that are very commonly used in chemical engineering. So imagine I have a tube where fluid can flow in, and at one point in the tube, there's sort of a grate that fluid could flow through, but large particles couldn't. And then just upstream, right? So I'm flowing fluid through, and just upstream of this grate that I have here, I have a bed of beads or particles. And these particles aren't just any particle. If I were to zoom way in on one of these particular particles, if I were to sort of zoom way in and kind of exaggerate, you know, the scale of everything isn't exactly right here, but I have some bead or particle right here. And on the surface of this particle, I have some tether and some enzyme. So I have an enzyme attached to the surface of this particle, and maybe I have multiple ones. Right, so what's the benefit of attaching a whole bunch of enzymes to these particles? Well, these plug flow reactors are basically to have some type of reactant or multiple reactants come in, have them undergo some chemical reaction, and then have them come out. And oftentimes in chemical engineering, whatever chemical reactions we have need to be facilitated via enzymes, right? They don't just happen necessarily spontaneously or happen very quickly at room temperature. So we flow them past beds of particles with enzymes. And you know, so what's the goal here? You know, you have reactants come in, the flow, you know, trickles through all of these particles where the enzymes can react with the reactants to produce products, and then the products are flushed downstream. But what's the benefit here? Because these enzymes are tethered to the surface and these beads are blocked by the grate from flowing through, the enzymes remain here the whole time. The alternative to a plug flow reactor would be to just mix in the enzyme, you know, would just be to have some vat where I mix in the enzymes and they're just sort of freely floating around. But you can imagine if I have my enzymes mixed in and they're freely floating around with my reactants, then I need to have some process later on where I try to, you know, to extract out or to separate out the enzymes from my desired products. And maybe I can do that successfully, maybe not. The other thing is oftentimes these enzymes are expensive. It's, you know, it might be costly to produce these enzymes. So if I can keep the enzymes from flowing downstream with the products, then I can use those enzymes as long as I want. And they can, you know, they can serve their function over and over and over and over again. And that, you know, that essentially becomes a one-time cost rather than a continuous expense. So these plug flow reactors are super important. How does that, why is the tethering of the enzyme important to us? Well, we need to tether this enzyme in such a way that it doesn't interfere with the protein's ability to do its enzymatic process, right? So if we tethered it in a way where it couldn't, you know, do whatever conformational changes or couldn't properly bind to the reactants, you know, if we tethered this enzyme incorrectly, then it wouldn't be able to serve this function. Or if we tethered it too loosely, then it could, you know, separate off from the surface and get flown down with the products, and we wouldn't want that either. So plug flow reactors oftentimes are used in chemical engineering and bioengineering to serve these purposes. Another application that I'd talk about is, so in general, so last time we talked about how plasma treatment could make a surface more hydrophilic, and how making a surface more hydrophilic can make it, can reduce protein adsorption and potentially, you know, reduce thrombosis or reduce a, you know, cell adhesion in an immune cascade. But we can be even more effective than plasma treatment with certain cases by tethering specific molecules. So for example, you can coat a stent or a catheter or some other blood contacting device or implant with heparin. And if you go back in your notes to the lecture we had on natural polysaccharides, heparin was one of them. And heparin is a very, very hydrophilic molecule. So you can have some surface that wouldn't ordinarily be hydrophilic, coat that surface with heparin, and then all of a sudden whatever blood or proteins in the blood or cells in the blood are contacting that surface. Now they're touching the heparin instead of the surface that would promote protein adhesion. So basically you can block protein adhesion by coating a stent or a catheter with heparin, and this basically makes it less thrombogenic. So heparin can often, break down after a while. It doesn't last forever, and also, it can be sort of finicky as it's a biomolecule, or potentially expensive to produce and purify. There are other other hydrophilic molecules that you can graft to the surface of things to sort of similarly reduce protein adhesion or reduce thrombogenicity. So we can reduce protein So we can reduce protein absorption by grafting or growing PEG, aka polyethylene glycol. And what does polyethylene glycol look like? Well, I'll draw its molecular structure. The molecular structure of PEG looks like this. So I'll use the organic chemistry shorthand. So there's an oxygen, single bonded to a carbon, single bonded to a carbon, single bonded to an oxygen, carbon, carbon, oxygen, carbon, carbon, oxygen. And of course, all of these carbons have secret hydrogens attached to them. So when I think about, which bonds might be hydrophilic, any of the oxygen-carbon bonds are going to be hydrophilic, right? So this bond's going to be hydrophilic, this bond's going to be polar, which results in the molecule being hydrophilic. So polar bond, polar bond, polar bond, polar bond, polar bond, polar bond. So, many of the bonds in PEG are polar. Which basically means this PEG molecule is very hydrophilic. And very hydrophilic molecules reduce protein absorption. So what might that look like? You might have some surface here that would otherwise be hydrophobic, and if you can basically grow or graft a brush of PEG on the surface, then any protein that's in your fluid basically can't adsorb to the surface because the PEG is blocking it. So that's why we might want to why we might want to graft PEG onto a surface. And if you don't believe me about how PEG is very hydrophilic, well, you can just look at how PEG is used in some medicine. So right here, I have some Miralax, which is a stool softener, and it relieves constipation and irregularity. And what is the active ingredient in Miralax? Well, nothing other than polyethylene glycol, and this 3350 number is the molecular weight of the polyethylene glycol used. And so, here it is, the active ingredient. And, each dose, you're supposed to have 17 grams of this stuff. So this Miralax is basically this powder, and you're supposed to have 17 grams of this powder. when you consume Miralax. And what does it do? It's basically these big long hydrocarbon, or these big long polyether chains that are very hydrophilic. And what it does is, it passes through your gastrointestinal tract, and your body doesn't really have too much that can break down PEG on the order of a couple of days. So it basically forms a hydrogel in your poop and makes your poop nice and soft and hydrated and, easier to pass. So it's less stiff. So for the same hydrophilic reasons why PEG is used as a stool softener, the hydrophilicity of PEG is also used to bind to surfaces to grow polymer brushes that can basically reduce protein adsorption. So what's another example of an application where we'd want to graft a molecule to a surface? So let's talk about immunoassays. And the word immuno basically means, hey, there might be something related to immune systems. So what is an immunoassay? You basically have some surface, and you attach to that surface antibodies. So antibodies are basically these molecules that are in our immune systems, and they sort of stick to foreign invaders. And oftentimes what they do is, they basically serve in some way as a kind of memory for our immune system, where we have a whole bunch of different antibodies in our bodies that are specific to diseases or pathogens or molecules that we've encountered in our past. So an antibody might look like this, where there are sort of little active sites on its surface, and these active sites are specifically bind to one type of molecule. So these antibodies are basically very specific to some molecule. So we have some site on an antibody, and this antibody might have one or more sites that are very specific to a molecule of interest. So what can we do? We can tether that antibody to a surface, and with an antibody tethered to that surface, then we have a surface that's very sticky to one particular type of molecule. It's very sticky to one particular type of molecule, but not particularly sticky to other types of molecules. And this is very good for looking at, for trying to detect the presence of very specific analytes. So for example, one example of an immunoassay that people might have encountered, or maybe had friends or family members who encountered, is a pregnancy test. So a pregnancy test, there's basically a strip with particular antibodies tethered to the surface, and the antibodies are very sticky to a hormone that really only gets released in appreciable amounts when when the embryo has implanted into the wall of the uterus. So basically, and that molecule is present in the urine of the mothers. So you can basically flow some urine past this surface. Antibodies are tethered to that surface, and the antibodies stick to the particular hormone that's present. Oftentimes what you can do is you can sort of do what's called a sandwich assay. Where you basically have your surface, you have a tether and an antibody, one type of one antibody, and that antibody might stick to your particular molecule of interest, and then only when this molecule of interest has stuck to this antibody will a second type, you can then flow a second type of antibody past. You can flow a second type of antibody past that surface. That in this second antibody only sticks to the complex of the first antibody and the particular molecule of interest. And this second antibody that we stick to the surface oftentimes has some kind of fluorescence some kind of fluorescent marker or some dark dye on it that's visible. So basically during the pregnancy test, the urine flows by, the molecule sticks to antibodies, and then there might be some secondary antibody or whatever that sort of sticks and either, for fancy ones has fluorescence readout, or for less fancy tests just has a very dark molecule attached to it. So you can basically see the strip appear or not appear. So basically, but how does this impact us? Well, you basically want to tether the antibody to the surface in such a way that the antibody's tethered on some non-critical part of the antibody and not on the active site, but also tethered with just a single tether, so the antibody can kind of remain free to grab onto the molecule of interest. So one application that's actually a little closer to some work that I did is beyond using antibodies to just grab onto particular molecules of interest, you can use antibodies to capture entire cells. And this was some work that my colleagues worked on when I was a PhD student. So one more example is in cell capture. So we can use antibodies to capture entire cells. And the work that we did was in this geometrically enhanced differential immunocapture. So, or we called it JEDI for short. So how does this geometrically enhanced differential immunocapture work, and how is it related to tethering molecules to the surface? So picture, so this is a microfluidic device where we would basically pump through just 1 milliliter of patient blood. We would basically develop this device to try to capture particular cells. So first, let's talk about the cells we want to capture, and then we'll talk about the device and what it is. So if a patient has cancer, that cancer oftentimes, well, not blood cancers, but most sort of epithelial or tumor-based cancers start with a tumor, and that tumor can shed cells into the bloodstream. And like cancer's awful, right? And but one of the things with most epithelial cancers is it's usually not the primary tumor that poses the most risk to the patient, but the risk of that cancer metastasizing and forming not just one primary tumor, but forming lots of tumors all over the body. And this is one reason why cancer is awful, is that it has epithelial cancers possess the ability to form distant metastases, distant tumors elsewhere in the body. It's unknown for certain, but it's definitely possible that it's these cells that are shed into the bloodstream that could be responsible, at least in some cases, for forming distant cells. So what can we do? If these cells are present in the bloodstream, we want to capture them. We want to capture these cells. And if we capture these cells, we'll be able to do a couple of things. Thing number one is just by counting the number of cells, that can correlate with prognosis. Generally, if there are more circulating tumor cells in the blood, the prognosis of the patient is poorer. A second thing that we can do is we can assess whether the person's chemotherapy is working. So you can basically capture some of these cells that are circulating in the bloodstream and then look at the captured cells in your device with the microscope, and you can say, hey, based on the staining and the sort of morphology and profile of the cells, you can say, hey, is this chemotherapy actually working to kill these cells or not, right? Have the cells, has the cancer evolved some sort of resistance to whatever type of chemotherapy you're using? And that could inform a switch. right? This might inform whether you'd want to switch to a different type of chemotherapy. And the other thing you could do with this is you could personalize, right? So before you even start giving a cancer patient chemo, you could capture some of these circulating tumor cells and split them into a couple different batches, and then hit each batch with a different type of chemotherapy to see what kind of chemotherapy is going to kill that person's cancer the best. Or perhaps even all three of these. And one of the most important things you can do, or one of the benefits of looking at the circulating cells rather than looking at the tumor, is it's perhaps these cells that are the most important to kill, maybe even more important than killing the primary tumor. And a lot of times with epithelial tumors, the clinicians take out the primary tumor. So you need some mechanism to capture and assess and investigate any cancerous cells that might be remaining after you've taken out the primary tumor, i.e., did we get the whole thing? So what is this microfluidic device? Why is this investigation of capturing cancer cells? How is this important to tethering molecules to the surface? So let's take a look. What is this microfluidic device? Well, imagine zooming way, way, way in on this microfluidic device. And the device that my colleagues developed was essentially this array of posts. And just for a sense of scale, the diameter of these posts was on the order of 100 micrometers. So super tiny. You can't hardly see these posts at all. And then we would flow blood through this array of posts. So there would be a bunch of blood cells, right? White and red blood cells, let's say, but there also might be some cancer cells in some circulating cancer cells in the blood as well. And I'm exaggerating the number of cancer cells. These cancer cells, there might be a dozen or a couple dozen cancer cells in a milliliter of blood compared to 10 million white blood cells or a billion red blood cells. So this is a needle in a haystack problem. So we have these posts. We flow the blood through the device, and we want most of the blood cells to sort of flow right through the device, uncaptured. But we want our cancer cells, when they flow through the device, to encounter the posts and get stuck. And it turns out that cancer cells tend to be a little bit bigger than blood cells. So we basically had this situation, we designed the geometry of these posts very carefully, where each set of posts was offset a little bit, where cancer cells, after bumping into a post, due to their larger size, would be displaced onto a fluid streamline where they encountered all of the posts over and over and over again. So the cancer cells would bump onto, as soon as they bumped onto one post, would hit every subsequent row of posts. Whereas blood cells, being a little smaller, if they bumped into a post, they would be displaced onto a streamline. If a blood cell encountered a post, it would be displaced onto a streamline that basically missed all of the remaining posts. So cool fluid mechanics, cool engineering went into the geometrical design of this post. Some cool chemical engineering and bioengineering went into the sort of chemical design of the surface of this post. And that's the most relevant part of this lecture. So imagine I have this post. What could I do to this post? Well, I could tether antibodies to this post. So in the same way that we tethered antibodies to look for specific molecules in an immunoassay, if we're looking at using immunocapture to capture cancer cells, we could decorate our posts with antibodies. We could decorate our posts with antibodies and make these antibodies very sticky to cancer cells. So we could make these posts very sticky to cancer, but make these posts not particularly sticky to blood cells. And the benefit of cancer is you know that it might be coming from some particular organ in the body. So for example, if you have prostate cancer, those prostate cells have a bunch of proteins on their surface. These prostate cancer cells have a bunch of proteins on their surfaces that are unique to being prostate cells. And blood cells lacking those proteins would not be particularly sticky to these surfaces, whereas prostate cells with those proteins on their surface would have a very strong affinity to these antibodies. So basically, you can make the chemistry of your posts such that cancer cells stick and blood cells don't really stick. And you can design the geometry and the fluid mechanics of the post such that cancer cells bump into the posts over and over and over again, whereas blood cells flow right through. Why is this? So from a chemical aspect, we basically need to design linkers between the post and the antibody to link the posts to the antibodies in such a way that doesn't disrupt the antibody's ability to bind to the cancer cells. And that's kind of, that's sort of similar in spirit to the rest of the applications that we talked about. All right, so thus concludes our discussion. This concludes our discussion of applications of strategic modifications of surfaces via chemistry. And now we'll sort of talk about general goals of modifying surfaces chemically. So what general goals do we have? We can break it down as follows. In general, it's usually, and we'll sort of talk about the typical goals. Of course, there are exceptions, but usually we want to coat that surface densely, right? So for example, if we bring it back to this cell capture thing, the more densely I've coated this surface with antibodies, the stronger that whole surface, right? I might get multiple antibodies clinging onto that cancer cell, right? So the more dense I have these antibodies on the surface, the more likely that cancer cell is to get captured rather than flown through with the blood. The second thing is we need to avoid tethering on active sites of antibodies or enzymes. Right, so if we sort of look at this kind of canonical view of what an enzyme looks like, right, so if there's some enzyme, it would be a lot better to tether that enzyme to the surface on some non-important site, because you can imagine if I had some enzyme and I tethered that enzyme to the surface via the active site, then any reagent that enzyme, the reagent couldn't really fit in there anymore, right? So if I tethered to the active site of the protein, or either the antibody or the enzyme, then whatever molecule that protein is supposed to bond to no longer fits in there, right? So we want to avoid this situation and allow this situation to occur. The final thing we want to do, so usually we want to coat surfaces densely. We want to avoid tethering on the active sites of antibodies or enzymes. And finally, we want to avoid over-tethering. So what do I mean by over-tethering? Well, let's say I had some surface here, up until this point, I've kind of drawn the ideal scenario, right, where I have some enzyme that has a single tether to the surface right here. But these proteins are basically, these proteins are essentially sequences of amino acids. Like they themselves are coils and sheets of protein. And if I over tether that protein to the surface, you can imagine if I have some enzyme here and I try to attach too many tethers to that protein, so oftentimes when antibodies or enzymes, when they're binding to our analyte of interest or our cell of interest, they need to undergo some conformational change. And over-tethering prevents binding, maybe prevents conformational change. So if I've over-tethered this protein to the surface, maybe I will have inhibited this this analyte's ability to bind to the surface or bind to the active site of the protein, or I've inhibited the protein's ability to catalyze some reaction. So usually we want to avoid this as well. So this concludes our discussion of sort of general goals, right? Things we want to have happen, we typically want to coat the surfaces densely. Things we don't want to have happen, tethering on the active site of an antibody or enzyme, or over tethering a protein. And of course, we'd want to avoid under tethering too, where we try to attach a bunch of antibodies to the surface, but we only get a couple, right? So we don't really want to have either extreme happen. So thus concludes our discussion of general goals. Now let's sort of talk about the general idea of the chemistry, right? How do we go about forming such a tether, right, between a surface and between an enzyme? Let's talk about the general strategy. So strategy for linking. And we'll sort of talk about this as kind of a series of steps or a series of things you need to understand. So in general, we have some surface. And we have, let's use the particular case where we want to attach a protein to the surface, whether the protein is an enzyme or the protein is an antibody. Let's talk mostly about those cases, right? So we have some surface and we have some protein. We have the surface and we have some protein. So the first thing that we need to consider is what functional groups are on the surface, what functional groups are on the protein. And if we think about proteins, most proteins, so if we kick it back to our biochemistry days, right, we might think most proteins have some COOHs, right, some carboxylic acid groups on them, maybe multiple carboxylic acid groups. They might have some amine groups. They also might have some thiol groups or sulfhydryl groups, some SH. So proteins, oftentimes have one or more of these functional groups sticking out of the surface, right? And some of them, different proteins might have different active groups in their active site, right? So let's just pretend that this protein, the active site on this protein, is, is this part of it that has these COOHs on it, right? So if we're thinking about how do we want to attach this protein to the surface, we don't want to use some kind of linker that is going to react with COOH groups. We perhaps would use some kind of linker that maybe reacts with these SH groups or these NH2 groups. Another thing we might want to consider is what type of surface are we trying to bond this protein to, right? So we've talked about a lot of biomaterials, both synthetic polymers as well as quote unquote natural polymers. And, oftentimes these surfaces might have lots of functional groups too, right? So, I won't list, we'll talk in more detail later on about all of the details of what types of functional groups could exist on the surface. But just know that, the surface might have SH groups or NH2 groups or COOH groups or, potentially more different types of proteins as well on that surface, right? So the surface has some functional groups, the protein has some functional groups, and we basically need to create a link between them. All right, so let's just sort of abstract, regardless of whether it's an SH or a COOH or an NH2, let's just say the protein has some molecule on its surface that, is, let's say, a circular shape. We're just kind of abstracting things here. So let's say there's some circular shape on the protein, and let's say the on the protein, and then let's say our surface over here has some functional group that I'm kind of abstracting as a diamond shape right here. If we have some linking molecule that we could put in to this mixture, let's say there's some hypothetical molecule that is what we'll call difunctional. So is there a difunctional molecule that can link? Is there some difunctional molecule that can link? So what might that difunctional molecule look like? That difunctional molecule might have one functional group on it that's very sticky to the functional group that's present on the surface, and it might have some other molecule or some other functional group on it that is very sticky to the protein, right? So this difunctional molecule can basically create a potentially covalent bridge between those. So it has one functional group that reacts to form a covalent bond with whatever functional group's on the surface, and another functional group that can react to create a covalent bond with whatever's on the protein. And sometimes, if just a single difunctional molecule doesn't necessarily exist to bridge this gap, maybe we can create a sequence to build up, right? So let's say I have a surface here, with my diamond-shaped functional group here. I have my protein here with my circle functional group right here. Maybe this hypothetical magic red molecule doesn't exist, but there's one molecule that's very sticky to this diamond functional group, and then a separate molecule that, let's say, has a square that's very sticky to something on this one linker molecule, and then another site that is sticky to the protein, right? So we might want one or more intermediate linkers. If there's one intermediate linker, great, that might work. If there's another intermediate linker, then then we might need one or more steps. And we finally, sort of consistent with our general goals of, under tethering or over tethering, of tethering to the active site, right? If tethering to the active site, we might want to choose the right difunctional molecule to react with part of the protein that's not part of the functional site. We also might want to consider another advantage of a sequence to build up is to get a appropriate length. Oops, make sure you can see that. Right, is we want an appropriate length tether. So, if we have some surface with our protein, our linker, and our protein is very close to the surface, that protein might not extend out far enough into the bulk to capture cells or to react with the reagents we want to. Under some circumstances, we might want a really long tether to try to get that protein really far out there, either so the protein can keep its proper conformation or so the protein can just sample farther into the bulk of the fluid flowing past it, right? So a sequence to build up to the protein could accomplish two things. One, it might not, a single molecule might not be available to serve that function. And then the other thing is a sequence we could build up a longer length to basically have the protein farther out, which might inhibit the protein's conformation less, as well as allow the protein to reach into the bulk fluid more. So up until this point, I've kind of hinted at some quote unquote functional groups that might be able to participate in the linking. These are some ones that are present on the protein, but what are these abstractions here? Like, what is this diamond? What is this thing that looks like the opposite of a diamond? What is this circle? What's the thing that looks like the opposite of a circle, right? What are some examples of actual chemicals that can accomplish, this bonds to this bonds to this bonds to this, and then we're happy, right? So what are some molecules that can actually accomplish these bindings? What are some functional groups that, that if you had a molecule that had two different functional groups could serve as a linker? Let's create a little chart. So now we're giving examples of functional groups and what the interactions between these functional groups are, i.e., what are the diamonds and what are the things that could bind to a diamond? All right, so you can pause the video if you want at any point to look at. We're gonna talk about like a whole bunch of different chemical groups. You can pause the video at any time you want if you want to write down the chemical groups, but you could always just look them up. A lot of these molecular structures are on Wikipedia and things like that. So I'm gonna just sort of information dump a whole bunch of chemical groups, how they react with one another, and when they might be useful in the context of strategically attaching chemicals, and in particular proteins to surfaces. So let's talk through this list. So I have a list of 11 or so molecules, or 11 or so functional groups, and how they might be useful in attaching molecules to surfaces. So the first on this list is silanol, which is basically silicon with an OH group on it. And of course, the silicon might be attached to a couple of other things as well, but there's basically silicon and there's an OH group. And silanol forms basically when you have silicon, like for example, a silicon wafer, or maybe even some silicone from PDMS. This OH group spontaneously gets attached to any exposed silicon atoms because if water encounters a silicon surface. So basically, if you have silicon that contacts water, you're going to get silanol on it. What can the silanol react with? Well, the silanol can basically react spontaneously with a different chemical group called trimethoxysilane. And so what is trimethoxysilane? You basically have some silicon molecule with silicon oxygen and then a methyl group. So this trimethoxysilane basically has one bond that could go, somewhere else, and 3 bonds that have these methoxysilane groups. So what does this look like? So let's say I had my silicon surface. If I had some silicon surface, there's going to be a bunch of silanol. There's going to be a bunch of silanol on that surface. And then if I bring in some linker molecule that has trimethoxysilane on one side, so let's say there's CH3, So if there's a trimethoxysilane, some linking molecule that has a trimethoxysilane on one part of it, and then, you know, let's say some chain that belongs to the fourth bond of the silicon, and then maybe a third functional group, let's say, for example, thiol, then this molecule right here serves the purpose of, this molecule right here essentially serves the purpose of what we were talking about here, where the surface has one functional group on it, and then we could put a difunctional molecule in the middle. For example, a molecule that on one arm has trimethoxysilane, and then on another arm has this SH group that could be potentially available to do some other bonding, right? So, so that's why we might have some interest. And it turns out that this silicon surface with this trimethoxysilane, these two react with one another. So here I have this column, you know, reacts to form a bond with. You know, these essentially react to form a bond with one another. And what I'm going to do, actually the yellow isn't super visible. What I'm going to do is I'm going to highlight in orange any of these bonds that are spontaneous. So it turns out that if trimethoxysilane encounters silanol, then it spontaneously, boom, it forms a reaction. You know, we don't need any enzymes or unique chemical conditions in order for this bond to form. So basically, if I wanted to attach a protein to a silicon surface, I could have some linking molecule that has trimethoxysilane on one part, and then something else that could react with protein or could react with something else that reacts with the protein on the other arm. So the trimethoxysilane and the silanol bond is spontaneous at room temperature. And let's say if hypothetically we had this molecule here, we could have this SH group that could potentially form a bond with something else. So now let's talk about SH groups, thiol, aka mercapto, aka sulfhydryl. So these SH groups can actually react with themselves to form bonds, but you know, if I just had a whole bunch of this molecule present by itself, you know, the SH groups don't react with one another spontaneously at room temperature, right? So these SH groups don't react with one another spontaneously, but they can react with one another under certain conditions. So for example, like SH groups can react with other SH groups on the side groups of protein chains, and that's actually one reason how our hair, how proteins in our hair or proteins in our collagen can actually get crosslinks. So SH group can form crosslinks, but that process is not spontaneous at room temperature. One thing that SH groups can bond with that's spontaneous at room temperature is this group over here called, I'm not exactly sure how to pronounce it, malamide, something like that. And it looks like this. So for example, if we had a silicon surface, we had a trimethoxysilane group and an SH group. So we basically have our silicon surface. We then put this molecule on the surface here, leaving the surface with a bunch of SH groups. If we then put in a molecule that had malamide, on it, this would react with the SH group spontaneously at room temperature to form a bond. And so if we wanted to sort of, build up some linking thing, we could also, for example, have a molecule that on one side has this malamide, and on the other side, let's say, has NHS. So So there could be malamide on one side, and there could be this other molecule that I'm going to talk about now. So there's this molecule, NHS. The NHS stands for something, but it's basically this functional group right here. And this NHS group reacts spontaneously with amine groups. So NHS can react spontaneously all the way down here. Sorry, I'll show you the bottom of my list. But NHS reacts spontaneously with amine groups to form a covalent bond. So, if I had something with an amine group on it, then I could attach that surface. And for example, this one example of a type of protein that might have an amine group on it, almost all proteins have an NH2 group on it. So if I just wanted to attach proteins to this surface, I could sort of build up this sequence of events. And if I wanted to be very careful about it, I might want to very carefully control the concentrations of these various things. I might want to only put so many on the surface that I don't over-attach to the protein here, right? So I could basically have my silicon surface. I could put this molecule in blue on it, where one of the functional groups reacts with the silanol and the other can react with melamine. Then I could have a molecule that has melamine on one side and NHS on the other side, and the NHS on the other side would be free to react with the amine groups of the protein. And this would essentially allow the protein to have a bridge to this surface, even though amine groups wouldn't directly react with silanol. So let's just identify a couple of other things that I have on my chart. There's avidin, which is this sort of, I won't sketch it out, but it's this small to medium-sized protein. It has a strong affinity for this other molecule, biotin, which I've sketched out here. Biotin and avidin can basically form a it's not a covalent bond, but it's some bond that's almost as strong as a covalent bond. And then that happens spontaneously at room temperature. One cool thing about biotin is you can oftentimes buy a lot of antibodies that are pre-biotinylated. So there's some antibody that you want, and the supplier of that antibody has already attached a biotin to that antibody and attached the biotin in a place on the antibody that doesn't interfere with the antibody's active bonding sites. So if they're available to you, buy those pre-biotinylated antibodies, because they can do that, right? So for example, instead of trying to attach your antibody directly to the surface, you could attach avidin to the surface via this chemistry, and then you could buy a biotinylated antibody that would stick to your avidin. That could attach to your avidin right here, right? So you can have a biotinylated antibody, you could build up to avidin via this chemistry, and then boom, you can attach antibodies to a surface. All right, so that can work really well. Some other functional groups that we might want to consider is carboxylic acid. Carboxylic acid does react with OH, right? Remember when we talked about carboxylic acid reacting with OH to form an ester bond, but that only happens at really high temperatures, things like that, right? So if you have OH and carboxylic acid just bumping around with one another at room temperature, they're not going to form a bond. Carboxylic acid groups, we also know, can react with amine groups, although they don't form covalent bonds spontaneously at room temperature, right? I mean, if they did, then all of the proteins in our bodies would spontaneously form. If we think about proteins, all of the proteins in our body would react, the carboxylic acids on one would all react with the amine groups on the other, and we would just be this horrible cross-linked mess. I didn't sign up for that, so, that happens, right? So there we have it. So amine reacts with a lot of stuff, some of it spontaneously at room temperature, but others not spontaneously at all. Amine groups can react with aldehydes spontaneously at room temperature. When we talked about glutaraldehyde as a cross-linker, glutaraldehyde is basically a molecule with two aldehyde groups on it, so it can cross-link one amine to another amine. So there we are. If we think about this chart that we have here, some of these happen spontaneously at room temperature, some of them don't. but all of them might be useful in some context towards building up from one surface type to another. Right? Our surfaces aren't always going to be silicon, right? Our surfaces might have other functional groups, but we can sort of use this idea of, X links with Y, A links with B, but B doesn't link with Y to sort of build up a sensible sequence to attach molecules to surfaces. All right, so thus concludes our discussion of examples of particular functional groups and their interactions. So now let's move on to sort of recap some of those interactions, but explore a little more deeply the importance of concentrations on how successful this process is going to be, as well as the importance of order of operations on how successful this process is going to be. Let's talk about order of operations. I know I said I'd talk about concentrations first, but let's actually talk about order of operations. So let's talk about order of operations and how important it is. And let's sort of talk about, how that's important for attaching this protein to this surface. Right, so when we talked about proteins, we said, yeah, a lot of proteins have NH2 groups, but many, many, many proteins, for example, have multiple NH2 groups sticking out. And they also, a lot of proteins also have SH groups sticking out, and they also have COOH groups sticking out. So proteins are kind of this, this big mess where there's just tons of different types of groups sticking out. So let's see how order of operations would affect this sort of sequence of buildup that we had here. So I described the process of having the silicon surface and then attaching this molecule to the silicon surface and then this molecule to the SH that was on this molecule, and then finally the protein to this surface, to this molecule right here. Just think for a moment, pause the video, and just think for yourself, what would happen if instead I took the protein, tried to attach this molecule to the protein, then tried to attach this molecule to the modified protein, and then tried to put that whole thing on the surface. All right, so let's, what would happen if I reversed? What would happen if I tried to reverse the order of these steps? So take a moment, pause the video, and consider. So what would happen if we reverse the order? Let's carry out this thought experiment, right? So here we have it. So let's say we had our protein, and this protein has, COOH, NH2, NH2, COOH, SH, SH, right? Let's just say it has a bunch of these groups, as do most proteins. So we have this protein kind of floating around, and this is the protein that we wanted to attach to the surface. But, it's not just one protein in isolation here. There's probably going to be other proteins with, also with SH, SH, COOH, NH2, NH2. And so what's going to happen? Well, we start off with this suspension of proteins, right? And if we followed the reverse step, we would then add a bunch of this molecule to the surface, right? So in this molecule, if you remember, was NHS and malamide. Again, I'm not sure I'm pronouncing that correctly, but and if you recall, this end reacts with SH, and this end reacts with NH2. So what implications would that have if we didn't care, if we were not careful with our order of operations? Well, I would put in this molecule, and the malamide part of it would react with the SH on one protein, and the NHS would react with the NH2 on the other. So what would happen? Well, before I had a chance to kind of get these proteins, attached to the SH groups that I want to on the surface, before that process even happened, I would be cross-linking these proteins with one another. All right, so what would happen is if I put this molecule in the wrong order, right, in the wrong way, then I would cross-link proteins too early and to each other. And that's bad. Right? What would happen is, you can imagine if I just had, you know, a protein and a protein and a protein and a protein, a protein and a protein, you know, all originally in suspension, you know, my goal was to have this case where I had the surface and I had all of my proteins individually attached to the surface via tethers. Right? This was my goal. Sorry, my goal was to have, you know, proteins in suspension. You know, my original goal was to have them attached to the surface this way, but if I did things out of order, if I did things this way, then my out of order, right? If I followed the wrong order for my procedure, then I would have my proteins. And before I even got to the step of tethering them to the surface, I would have cross-linked all the SH groups on one protein to the NH2 groups on another, maybe the SH2 groups on one to the other, to the other, to the other, to the other, to the other. You know, maybe I might have formed multiple cross-links between some of them, something like that, right? And what happens is I would just aggregate all of my proteins together, and they would just end up as this aggregated mess. Right, so there would just be this aggregated mess of all of the proteins, everything stuck to everything, and basically nothing would work. So order of operations is important. Why? Because if I go back to this step, where if I followed everything in the proper order, and you know, I had these SH groups on the surface, if I add this molecule to these SHs before the protein is even present, I can have reacted all of the SHs with all of the malamides, and then there wouldn't be any more of these available to cross-link proteins to one another, right? So I can basically apply these molecules in a proper sequence, make sure all of the previous ones are reacted before exposing the surface to the new one. And any unreacted ones, if I grow things up from the surface, I can wash them away before, I can wash away any unreacted reagents before they have a chance, you know, before I add the next thing and give it an opportunity to form an aggregated mess, like we talked about. An aggregated mess, like we talked about here. Okay, so forgive me for doing things a little out of order, but now let's talk about the importance of concentration of some of these linker molecules in the steps that we're going to do. The main thing when we're considering concentrations of various reagents is trying to avoid this problem of over-tethering. So, the importance of concentration. So, concentrate really hard on this section. So, if we think about concentration, so imagine I have my surface, and if we fall back on this very first step, where I wanted to attach some of this molecule, this linking molecule right here to the surface, I might want to pay very careful consideration to how much of this reagent I put on the surface, or in a sense, what concentration of this reagent I have in the, you know, in the suspension or in the solution that I pipette onto the surface, right? So I have the surface here, you know, how much of this should I put on the surface, right? And you can imagine there's this sort of Goldilocks situation where if I have too little of that linking molecule, right? If I have too little of this linker, then, you know, then there's only just then there's only just a couple of sites that I could attach my proteins onto. Right, then there are only a few sites that I can attach my proteins onto. So too little linker, and there's a low density of attached protein. Right. Too little linker, and there's a low density of attached protein, right? You know, maybe there's only one on the surface here. On the other hand, let's say I'm like, all right, well, I want to avoid this. I'm just going to put a ton of linker molecule, right? So let's say I, try to saturate. Let's say I try to saturate every silanol site with a trimethoxysilane, arm of a linker molecule. So I'm like, all right, not gonna make this mistake. I'm gonna just try to put as much of this on the surface as possible. If we do too much of this on the surface as possible, then, well, what happens is once I build all of this up to NHS, or even just, if the linker molecule could react directly with the protein, then there are essentially too many sites. There are too many sites that could link to the protein right here. So instead of having my protein with one nice tether on it, I've essentially over-tethered this protein. And, if it attaches once here and then once here, the sites could actually stretch out and deform the protein. So it deforms. It deforms the protein. So too much linker means it's over-tethered, and it could lose functionality. Right? Basically, the protein's no longer going to be able to carry out its binding or its enzymatic behavior if it's just attached at a million points. Or maybe even just 2 points might be enough to cause it to lose function. So there's this sort of sweet spot, in the middle where I have, where I basically have my tethers appropriately spaced, where I can get a pretty good density of proteins, and I can do that. And you can essentially calculate, you can basically calculate what is the size of my protein, what concentration of linker do I put in my reagents to basically give it such that the spacing, is roughly the size of my protein. Right? So again, the details of those calculations are kind of beyond the scope of what we're going to talk about here, but give or take a little bit, if you limit the density of your linkers such that the proteins are kind of evenly spaced, or proteinly sized spaced, then you're not going to have too much. You're not going to have a super low density of protein, which is means your surface isn't going to be as active or as sticky or as functional as you want it to be. But you're also not going to have this case where you've over-tethered the protein as well. All right, so that concludes our discussion of the importance of concentrations. So hopefully this lecture has been helpful to you in talking about some applications of applying chemicals to surfaces, some general goals that we might have in attaching things to surfaces, i.e. having lots of protein on the surface, but not so many attachment points that we mess up the proteins. The general idea of the chemistry of something linking to the surface and then another arm of that linking molecule attaching to the protein or attaching to something else that then attaches to the protein. We talked about some examples of these functional groups. There's a big long list, but some of these reactions occur spontaneously, some of them don't. And actually, just as an extra aside, some of these reactions, for example, an amine group reacting with the carboxylic acid group, if you put in some additional reagents, sometimes you can force these reactions to be spontaneous if you add in some extra facilitator molecule. So we talked about a bunch of functional groups, and hopefully there's some combination of functional groups that can end up attaching molecules from some surface to some protein, either an NH2, an SH, or a COOH usually on your proteins, or a biotin that someone else has already added to an antibody or an enzyme. And then we wrapped it up by talking about the importance of the order of operations, where if you don't do your order of operations right, then you end up just aggregating all of your proteins together and creating a horrible mess, and the importance of concentrations in achieving an appropriate density of the proteins that you want to attach to your surface. So thank you very much for listening. I hope you enjoyed this lecture.